All right, we're back. We're still on page 182. We're looking at parameterizing curves. And so far, we've done kind of two. There's only one problem that we actually did so far. But we also wrote this set of parametric equations. And so what I want to do right now is take this set of parametric equations and this set of parametric equations, put them in GeoGebra, make it move, see what happens, so that we get like a sense of what's happening. We said already that one of them kind of has a head start in the race. And let's see if we can like really make it clear what that means, because these are the kinds of things we need to think about. So I'm going to zoom out because x squared grows really fast. If I wrote the notes again, I might make it like x squared over 5 or something like that, just to like scale it down like the y values a little bit, but I didn't do that. So what are we going to do? First, I'm going to make a slider for t, and I'm going to say t equals 1. Okay, and I'm going to adjust this and have this go from like, I don't know, 0 to 5, let's say. All right, so far I've done nothing other than just kind of like set the stage, but you do a lot of that when you're trying to make these sorts of sketches. And I'm gonna drag this down a little and over. So to zoom, I like clicked on the, what did I click on? The minus, I think. I actually confuse minus and plus for zooming in and out, and I don't, it's hard to explain why I confuse those, but I do. All right, so what are we gonna do? I'm gonna just make a function called f of x equals x squared. The reason for that is that I can like really explicitly do the composition. So I'm going to turn it off because I don't need to see it. And now I'm going to use curve. So curve v. I'm using v because t is going to be the actual time. So I'm going to use v as my parameter. I can use anything actually, but I'm not going to use t because I want to do the following. So v is my parameter. F of v, right? So f of x is x squared. So f of v is v squared. So it's v comma v squared. X is equal to v, y is equal to v squared. V is the parameter. I want to start at 0, and I would like to go, well, let's start at like -3, -2, and we'll go to whatever t is. All right, so right now t is 0, so you can see the curve just stops there, and then if I increase this, you can watch it increase. So if t increases by 1, x will increase by 1, because x is just equal to whatever t is. So it's x is equal to v. The slope of that is 1, so a change of 1 in v corresponds to a change of 1 in x. So if I move this, so it's a little confusing because I'm using the parameter t. I'm using the parameter v, but then t is the upper bound of the parameter. So if I say t, I probably mean v, just to clarify. But when t changes by 1, x changes by 1. And then y changes by, you have to square it. So it's like a little less clear what's happening there. But think about what x is doing. So now my other parameterization is, so we're going to use curve again. I'm going to do v plus 3. And then f of v plus 3. So x is equal to v plus 3. Y is equal to the quantity v plus 3 squared, because that's f of v plus 3. And then I'm going to say v is my parameter. Let's go from -2 again, I guess, to t. You can already see that something weird has happened. Like, what is this gap? Well, the gap is because, let me go back to 0. The gap that's forming there, why can I see so much? Oh, because of -2. The gap is because when t is equal to 0, I add 3 to it, right? So it takes me to 3. So let's see, I think it'll be clear if I put points. But right now, it sounds like I don't know what I'm talking about because I'm kind of confusing myself. B of t. Okay, so both of these are in their respective positions when t is equal to 0. So when t is equal to 0, this point is here, this point is here. That's like the start of the race, right? And then, oh, I have an idea. All right, I'm gonna turn this on. Okay, so that's like the path that they're on. And then what I'm gonna do is I'm gonna alter these and just make these start at 0, because that's like way less confusing. U start at 0, and then why did you rearrange my graph? U start at 0. Okay, is this better? I don't know, maybe we'll find out. All right, here we go. So they're gonna raise. Every time t increases by 1, for both of these parameterizations, x will increase by 1. So that means that they're moving at the same speed horizontally. I mean, they're actually moving at the same speed, we just don't know how to prove that yet. But point B just had a head start. Like when t is equal to 0, point B is already at x equals 3. It's already just sitting there. A is at x equals 0, and then we increase it. The distance, the horizontal distance between them is going to remain the same. So this is like a race where B just has a head start. And eventually A is going to start moving quicker, but B is going to be moving even quicker. So it's never going to catch up. So that's what's happening here. Same speed, different starting point, same orientation. They're both going generally to the right. And that's all it is. All right. So I don't know if that went well, but either way, like hopefully you were following along and now you know a little more about GeoGebra, which is key to exploring these things. Let's do another parameterization, see how weird these can get. So if x is sine of t, so remember we're always doing y equals x squared. So if y equals x squared and x equals sine of t, then this must be sine squared of t. All right, so the domain, we said the domain of the plane curve is going to be the range of x of t. So if x is equal to sine of t, x can be anything between -1 and 1. So that's weird. That's like a very reduced amount of the curve. So instead of getting the full thing, we're only going to have between -1 and 1. Well, what happens to y equals x squared when we're between -1 and 1? So if this is y equals x squared, right? So it's x squared. So there and there. Y is just going to be between 0 and 1. So this is a really limited thing. So here we get this. So our sketch is much less. But something weird happens with this particular parameterization. So we can go all the way to 1, we can go all the way to -1, we can go up to 1 here, here, and then you just kind of draw y equals x squared. So can we put the orientation on this though? That's kind of the question. It's going to be hard. So think about it. So sine starts in the middle, right? So it starts in the middle, so you're going to be here when t equals 0. Then sine goes to a maximum, right? So if I just drew this, like a really crappy version of this, it goes to a maximum. So you're going to be here when t equals pi over 2. So at first, you're going to go like this. But when you get back here, you're going to go back to the origin. Then you're going to go to a minimum, then back to the origin. And it's kind of like a pendulum that we've made here. So this is really hard to put any sort of like arrow on. And it may be that this is not the best parameterization. But think a little more about it. What if we had made it 2 sine of t? It was 2 sine of t. Now we can go from -2 to 2. We get more of the graph, still a pendulum motion. So why not 3 sine of t? Then we go -3 to 3, and suddenly we're getting even more of the graph. So we can control a lot. But with this parameterization, we're always going back and forth, which is actually like a really interesting motion to like have access to. Let's go to GeoGebra and just see what that looks like. So if we change this to, I'm just going to keep adding. So I'm going to hide you. Okay, so we're going to do curve sine of t, comma f of sine of t, comma t. I'm supposed to be using v, so disappointment. V and v and v, and then we're going to go from 0 to t. Press enter. Okay, and then I need to put a point on that, so I'm going to say c of t. There's my point. Let's go back to 0. All right, I'm going to put this in motion. And maybe I will zoom in. Actually, let me just go home, right? And zoom in a little more. And so you can see this really kind of interesting motion that we're seeing here. Let me make this go from like 0 to, I don't know, 12 pi. So when you go 0 to 12 pi, it's going to like go faster because it covers the distance. I don't know what the ratios are. It's just like we'll try to go from 0 to 37.7 in the same amount of time it was going from 0 to 5. So obviously it's got to go faster. But look at this thing. It's just rocking back and forth, which is kind of cool. So remember, starting at 0, you're starting in the middle because it's sine. Then you go to a maximum, so which means you go to the right. And then from the maximum, you go back to the middle, then to the minimum. So we're going to start out in the middle, going to the right. And that's what happened. And then y doesn't have a choice. Y just has to follow y equals x squared. Whatever x is, it's got the squared. So it doesn't have a choice. It's kind of like a weird relationship. So this is, I think, a pretty strange choice of parameterization, but, you know, does the job. All right, let's see this. What if we use x equals cosine of t? So if x is cosine of t, this one's going to be really similar. This will be cosine squared of t. So the x is stuck between -1 and 1 because cosine is stuck between -1 and 1. And then if x is between -1 and 1, the graph of y equals x squared only goes from 0 to 1 on that interval. So we get that. So it's essentially the same graph. Man, do I wish that I had given you axes here. But it's like when you give people axes, you take away their their ability to decide what to do. So I don't really like that. So I don't know, I'm all over the place on that issue. I wish for my sake that I had taken away my right to figure out what to do. All right, so if x is cosine, cosine starts at a maximum, which means x starts at a maximum. The only way that can happen is if you're here at t equals 0, and you're going to be here at t equals pi over 2. You'll be here at t equals pi because the cosine of pi is -1, so x is -1 when t is equal to pi. Kind of makes sense. And then, so this one I feel like is more of a, like a skateboarding ramp where you like drop in like a half pipe. This is kind of that, like you're going to drop in. So you're dropping in from the right hand. If you want to drop in from the left, you'd have to start at a minimum to make it negative cosine. Let's go to GeoGebra and kind of play around with that and see if it's doing what we think it's doing. So what to do? I'm going to turn off this, turn off this. I'm going to add in a curve, cosine of v, comma, f of cosine of v. V is the parameter, start at 0, go to t. Okay, and then let me put this back at 0. And I need to put a point on there, so I'll do d of t. Okay, so that's where we're going to start. We're going to drop in and kind of go. And you can see it's just kind of rocking back and forth, which kind of makes sense. So, I mean, once you get a sense of what's happening, they start to you can feel what's going to happen, which is pretty good. And then you can start making kind of interesting looking things. Like, for example, what if I'm going to duplicate. So I'm going to hit the 3 button, the 3 dots, and then choose duplicate and just change this to negative cosine. And then I don't really need to change this to negative cosine because x squared is even, so f of negative x is the same as f of x, but whatever, I'm going to change it. It's just easier thinking about it. And then do e of t. And now when I put this in motion, you get kind of this neat thing where they're switching back and forth. This is where it starts getting a little artsy if you want it to, which I think you should. We can put a segment between D and E and just kind of watch that. And now it's growing and shrinking and so on. Just cool things. So this is the beginning of doing some kind of neat things. So let me pause this so that my computer doesn't catch fire. My computer does not like it when I'm running GeoGebra animations. I don't know why. Well, I mean, I don't know why, but I guess that it uses a lot of power or something. And then here's a weird choice, potentially. X is e to the t minus 1. Why on earth would I have done that? Well, let's first just do it. E to the, oh, got all the dots everywhere. E to the t, let me write. Oh, I crashed it. Let me see here. Get out, back in. Let's see how much we lost. I think we probably only lost the e to the t thing. We did. Woo. Okay, so x is going to be, oh, you know what it is? I didn't even crash it. I was writing with the eraser. E to the t minus 1, quantity, e to the t minus 1 squared. Domain could be a little tricky to figure out in this case. So what does e to the t minus 1 look like? Well, down at -1, and then it's basically e to the x. So it's going to look like this. So the range of e to the t minus 1 is negative, the range. Y is greater than, like, this is x, and this is t. So x is greater than -1. So that's interesting. So x is greater than -1. You can never get to -1. You can get infinitely close. If we're between, if x just has to be greater than -1, then you get all of y equals x squared, right? I mean, here's -1, circle, but you get everything. So I'm going to say that y is an element of the reals. The range is, generally speaking, I find harder to figure out. So then this, what's this going to look like? So x can be bigger than -1, -1, 1, but you can't get there. So open circle, strange. And it's like you can get arbitrarily close. So like as t goes to -infinity, we get closer and closer, but we never really get there. Strange. But this one has an orientation going this way, and it's fast, right? E to the t grows really, really fast. This is our fastest parameterization by far. So what I'm going to do, I'm going to take a look at this and then see, ooh, screen time reports. Oh, average. I'm looking at 2 different iPads. Oh, I don't even want to tell you. I don't even want to tell you. My total screen time, adding them both up, 543, is like 9 hours a day. But I mean, I do it, no excuses. I'd like to excuse it, but no real viable excuses. 9 hours a day? What? I do a lot of work on my iPad, but I also read exclusively on my iPad, like all the books that I read. So, I mean, a lot of it is reading. I read a lot, basically. But even like when I'm watching stuff, I'm still just like scrolling through Reddit or Twitter or whatever, like just on it all the time. Screen time. It's the modern plague, kind of. Well, that's kind of in poor taste because the modern plague is clearly COVID, which is actually the modern plague. All right, let's see. I'm turning off some stuff, and I'm gonna graph curve. I think that E just works. Maybe it doesn't. I'll do exp of v minus 1. So exp of x is e to the x, like on every program that you're going to use. So feel free to use that. And then this is v is our parameter. We go from 0 to 1. I got to go back to 0 though, unless it's at 0. Oh, coincidentally, it's not there. And then it's looking like I've interpreted this wrong. And why is that? So if what did e to the, oh my god, I got like the whole thing wrong. How did I get the whole thing wrong? Let me go back and think more about this for a second. Why is that wrong? Usually it's at 0. Oh, no, hold on. I think I didn't get it wrong. What I'm doing wrong right now is I'm starting at 0. Like if I started at, for example, like -100, I think it would fill, what? Negative, okay, so that definitely didn't work. Let me do like -1. Why does -100 not work? I don't know. I don't need to solve all the world's problems right now. -10. Okay, so I was plotting my curve from 0 to whatever, and we need negative t values to see that we're starting for some reason at -1. So like, whew, got it. Okay, so not really a problem, just a little weird. So I'm gonna start at 0 just because, I guess. And then I'll put a point on here, which will be h of t. And here we go. This is probably a long video of me just messing up. Well, why are you at 1? You're supposed to be at t. Okay. Now let's come back. And I'm gonna hit. So this is gonna grow really super fast. So here, how is that? Zoom out, like way out. All right, here we go. And go. Look at that. By the time t is equal to 2, we're like off the page. So this is a really fast parameterization. So if you're interested in how fast parameterizations go, I created a little bit of a race. Here we go, like a parametric race. And I got 3 things. So first, x is going to be t, then t cubed, then sine of t, natural log of t plus 1. So the reason I chose all of these is that when t is equal to 0, all of these will put you at x equals 0. So that's why it's a natural log of t plus 1. That's why it's e to the t minus 1. So when t is 0, we're starting at 0. And then what we can do, so I have parametrics for all of them, they're going to race to 25. And I'm just going to hit OK and see what happens. So you can see like some of these take off. A gets there eventually. What's A? A is probably, A is just x of t. So it's going to take until 25 to get to 25. No, it's going to take until 5 to get to 25 because it takes 5 to get to x equals 5 and then a squared to 25. So A is going to take that long. D is the natural log. Going to get there eventually, but it's going to take a really long time. C is the sine thing. It's just whatever. You can see B is like off the charts. Like this is the y coordinate currently for B. B is a t cubed, and then x5. Where are you? It's out here. It's going to be scientific notation pretty soon. So let's see. Let us speed this up. So you can see D is going to get there. Natural log eventually will get there. It just takes forever. But your parameterization matters. So this is definitely linked on the web page in the GeoGebra files. You can take a look at the parametric race and see like which one gets there first. How long does it take? We can actually solve for how long it takes. So I'm gonna do it. I know that this video is like 1,000 hours long, but let me just like really quickly. So basically all I need to do, because it's y equals x squared, all I really need to figure out is how long does it take x to get to 5? Because if x gets to 5, then y is going to get to 25. So x1 of t is just t. So if I solve, I know this is stupid, but if I solve this, I get t equals 5. So the first point will get there at t equals 5. The next thing was t cubed. So for t cubed, what I'm going to do is x2 is determined by t cubed. I don't really need to change these. I could just like change the solve. That would be faster. That gets there at 1.7-ish. So the first one, so 1.7-ish, x3, let me delete that. X3 is sine of t. That will never get there. X4, right? Because sine has a range of -1 to 1, so you never get to 5. So it's not going to happen. Natural log of t plus 1. This one I think is the most interesting. So to get to 5 takes 147.413. It just takes forever. And then x5 is e to the t minus 1. So x5 versus x2 is actually kind of interesting, to me at least, because I think exponentials are like crazy fast at growing. But this race isn't to infinity. This race is to 5. And so this actually, it takes 1.792 to get there, whereas the t cubed took 1.7. So actually point B gets there before point whatever goes with 5e. So if we go back and then I'll stop this video. We're basically done. I mean, we could have been done hours ago potentially. Where are you? Here we go. All right. So we said that one of the points will get there when we're at 5. So if I just make it 5, you can see point A is there. We said one of them gets there at 1.70, let's say 1.71. So I'm going to type in 1.71. Point B is there. And then 1.79, I think, is when E is going to get there, basically. And then 147 point something. So these are the sorts of questions we can answer. 147.4. We can create a race and we can hold the race and we can see when everybody's going to get to certain places. That's what parametric gives us that we just don't have if we're not using parametric. So I'm going to go back to the notes. This video ended up probably a lot longer than I planned, but that can't be true because I don't plan how long they're going to take. But anyway, when you choose, you determine the domain and range of the plane curve. You determine the orientation, right? Sine and cosine are weird choices because orientation, you just bounce back and forth. And then the speed, right? So t cubed, it turns out, for certain intervals will beat an exponential. So if you want to be the fastest, you got to really think about it. I'm going to end this here. I will come back in the next one and do some more stuff. I hope you find the GeoGebra stuff kind of interesting. I think you should play around with it. It can really help you understand this. Anyway, I will see you in the next video.